Well, good morning, everyone. And so I'm making this video after the lockdown announcement. So it looks like it's going to be 6 weeks rather than 2 weeks where we're doing this. But the good news is that we have evidence from last year with current year 13 that we can continue to cover the material effectively in this method, particularly if you are interactive and that you're coming forward by email or other methods with problems that you have. And I am very, very happy to spend, once I've made my lesson videos, to spend lots of time helping you out with individual problems. So please, resolve and commit to do that, as well as keeping up with the work. You can't leave it all till Friday each week. You need to follow your timetable as if you were in school. That's true with your maths videos as well as any other subject. We are due to move on to mechanics, but the start of mechanics, it's not complicated at all, but it's one of those things I'd rather be in front of you. So I'm going to defer mechanics. Those of you who do physics, it's not a big deal because it's a lot of stuff you've already covered. So I'm going to carry on with pure. Now, we like to break up pure maths when we're in the classroom, just because it provides a bit of variety. But I'm going to carry on with pure. It is probably the area that's easiest to deliver over this sort of medium. So we're going to carry on doing that. I'm going to start today just by reviewing proof, but we're going to move on fairly shortly. So we've looked at these proof methods now over these last few lessons and few videos. GCSE proof, proof by deduction, that's just using algebra. Proof of identities, where you've got your triple or equal sign and you lock one side and fiddle around with the other side. Proof by exhaustion, which I think is the most complicated. And then yesterday's, which I think is probably the easiest, where you just have to find one example that doesn't work. So I'd like to start by going through question 10, which is one of the questions from yesterday. I know the book had answers, but I'm always a little unhappy with their solutions. So we were asked to prove this statement. This is proof by deduction. So we're asked to use known facts to show that this is true when x and y are negative. And we've got an example answer, and we've got to explain the error made by the student. And the error they've made is that, unlike what we are supposed to do with proof by deduction, which is to start with known facts and to finish with the statement we're trying to prove, they started by assuming the statement they were trying to prove was true. And that's a no-no. You can't assume that this is true and then do some math to confirm that. You've got to start with something that you know is true and use it to end up with this. And as it happens, this one isn't true when x and y are both negative, as we're about to find out. So that was their mistake, and that's all you'd be expected to say. Explain the error. The student started by assuming the statement was true rather than starting with known facts. Now, we're being asked to prove that it's always true, and we're asked in part B to use a counterexample to show that it's not always true when x and y are both negative. So what we've got to do is to find one example of an x value and a y value that are negative that makes this not work. And actually, it's true. It's not true whenever for any negative values of x and y, but we only got to find one example. So I just used x is -1 and y is -1. So this side becomes -2. That's 1, that's 1, so the right-hand side becomes √2. So it's not greater than, -2 is not greater than √2, -2 is less than √2. So I suppose I really ought to just have the... So this statement is not always true. So we've proved by counterexample that the inequality is not satisfied. We're then asked, well, what if they're both positive? Can you do a normal proof by deduction? So here's what I did. I started with my rough working. I effectively redid what the student did. I mean, there's good maths there. So I squared both sides, expanded that, and got this statement here. And if x and y are both positive, then this is going to be bigger than this. Because if x and y are both positive, 2xy will be greater than or equal to 0. Now, it'll be equal to 0 if either of them are equal to 0. Now, do positive numbers include 0? Well, strictly no. So actually, I don't need the extra line there. I've only left it in because we've got the extra line up here. So if x and y are both positive, we know this is greater than 0. So this must be greater than this because this is greater than 0. And we know that if you factorise this, you get this because we did it here. And square root both sides, you get the thing that you're being asked to prove. So that's as required. So that's a standard proof by deduction. So before we move on from proof, I've just got 4 questions which are a mixture of the different techniques. And I thought we'd have a quick go through these. So here we've got a statement that we're asked to prove, and it's got a triple equal sign there. So hopefully you can recognise this is proof of an identity. So I am going to leave the right hand side and consider the left hand side. So I'm going to write consider the left hand side. And this is a statement with square roots in the denominator, which I know are not good. So I'm hoping that you're going to say, right, okay, in order to deal with that, I'm going to multiply the top and bottom by that. Because if it's square root of x minus square root of y, if you multiply by the square root of x plus the square root of y, nice things happen. And I need to do that top and bottom. So go on, pause the video at that point to see what happens when you do that. We're hoping that we end up with this. That's what we're being asked to show. Let's see if that does work. Okay, so I've expanded the top, and that looks horrible. I've got x times root x and minus y times root x, and there's no simplifying here at all. So, oh dear, right, that's worrying me. So now I'm going to multiply out the denominator, which I know is going to be good because this is, we're rationalising here. So I know this is going to end happily, and it does because you get root x times minus root y is minus the square root of xy. And root x times root y is the square root of xy. So when you peanut those two, they cancel out. You've got square root of xy, take away the square root of xy. So all you're left on the bottom is x minus y. Can you see what we do? I don't need to worry about this, do I? Because if I put that in a bracket and just leave the top as it is, I can cancel out my x minus y. And so I'm left with, which is what I was hoping I was going to do. So it's quite a fiddly one, but there we go. And you know, if I'd tried to sort of simplify it from here, I would have got in a mess. So that was why it was worth multiplying out both, and then just using a little bit of common sense, and always keeping an eye on what I was trying to aim for. Okay. What about this next one? This is a proof by exhaustion question. So again, press pause and see if you can have a go at this one. So sometimes proof by exhaustion questions require you to consider odd or even numbers separately, or we had that horrible one yesterday where we had to consider multiples of 3, one less than a multiple of 3, one more than a multiple of 3. But sometimes you actually try all the possible values, and in this case we're talking about odd numbers less than 10. Well, there's only 5 of those, and we've got to show the sum of 2 consecutive positive odd numbers less than 10 is always an even number. So, well, there's only 4 sums I can do. I could do 1 plus 3, 3 plus 5, 5 plus 7, 7 plus 9. All of those give an even answer. So that was it. That was all I had to do. So that was quite an easy proof by exhaustion question. Here's a statement that we are being asked to show is untrue. The statement says that this is a prime number for all values. So if we can find one value that doesn't work, then we've shown it's untrue. So this is a disprove by counterexample question. So I don't know whether you want to use your table function on your calculator or just try different values yourself. Have a go at that one. Okay, so I used table function. I entered it and tried values from -5 to 5, and I've got when n, no it's not x, it's n, is -5, you don't get a prime number. When n is -3, you don't get a prime number. When n is -2, you don't get a prime number. When n is 3, you don't get a prime number. So I'll use that one. I'll say when n is 3, 3 squared minus 3 plus 3 equals 9, which is not a prime number. So the statement is not always true. Well, actually, I'm going to put, they say show it's untrue, so the statement is untrue. Now, sometimes you get a question that uses the word prove, but it doesn't actually involve one of our proof techniques. So here's a question, and I'm hoping that this phrase here will straight away indicate to you which technique we actually need to use for this one. So this isn't a formal proof question. This is using one of the techniques that we've learnt earlier in the year. See if you can do that one for me. So I'm hoping you spotted this was a discriminant question. In this quadratic here, A is 1, B is minus k, alarm bells ringing there, and C is k. And 2 equal roots, that's a repeated root or one solution, so b squared minus 4ac must equal 0. So I plug in my values. Again, this is got to be really careful here. Minus k squared, 4 times 1 times k, a and c. Minus k times minus k is k squared, so you get that. I want to know when that equals 0. Well, it's quadratic, so I solve it. I solved it by factorising. It was a special case. So I get two solutions, k is 0 and k is 4, but we're told that k is positive. Remember, positive doesn't include 0. So k equals 4 is the only solution. So although that uses the word prove in it, we are, I suppose you could argue this is proof by deduction, but it's not the same sort of formal proof question as some of the other ones we've looked at. Okay, we're going to move on from proof. Proof rears its ugly head again in year 2, so we have an opportunity then, when we're fully vaccinated, to sort of go over this again, because there's one other proof technique that we need to cover in year 2. But we're going to move on. We're going to carry on with pure, as I said, and we're going to move on to something which I quite enjoy, so hopefully you will. Okay, so I'm not going to tell you what this next topic's called. I'm just going to sort of start by doing a few examples. So we can multiply out brackets, can't we? Double brackets. We've been doing it since year 7, year 8, whatever. And I'm a big fan of gridding it out. And so if you've got something like a plus b squared, we know that when we multiply it out, we get that. Often we don't have a's and b's, we perhaps have x plus 3 squared or whatever, but this is something we are used to doing. This thing in the bracket here is often referred to as a binomial. Binomial means two numbers. Bi, two, nomial, numbers, two numbers. And so what we're doing here is we are expanding a binomial. So this is a binomial expansion. Now, we haven't used that phrase before, but that's what we're doing. So what about a plus b cubed. Well, it's a bit of a pain, isn't it? Because you've got to do a plus b times a plus b times a plus b again. Well, good news is we've just done a plus b times a plus b, so all I need to do to work out the answer to that is multiply that by another a plus b. So go on, pause the video at that point and do that for me. All starting to look a bit fiddly, isn't it? I've got some rather odd terms in here. So here I've got 2ab times another a, so that's 2a squared b. Whereas here I've got 2ab times another b, so that's 2ab squared. But the good news is that when you come to simplify this, it's stripy, isn't it? So we've got a cubed, we've then got a couple of a squared b terms, a couple of a b squared terms, and then we've got the b cubed. So it's not too sad. So I've got 2 lots of a squared b and another lot of a squared b, so that's 3 lots of a squared b. And similarly, I've got 3 lots of a b squared. Now there's quite a nice symmetry to this, isn't it? So if we look at the pattern here, we started with an a squared, then we had an a times b, now we've got a b squared. And if we look at the coefficients, well, that's 1 effectively, isn't it? And that's 1 there, so it goes 1, 2, 1. And if we look at this, we start with an a cubed, then we have an a squared times b, then we have an a times b squared, and then we have a b cubed. So there's a pattern there, isn't there? There's a pattern in the way the powers of a change, and a pattern in the way the powers of b change. And there's a pattern to the numbers as well. If we think about the coefficients, effectively that's 1 and 1, so I've got 1, 3, 3, 1. Those numbers ring a bell. I mean, I'm a maths teacher, so this is the sort of thing I do. It may not ring a bell for you, but you may have come across a rather neat little thing called Pascal's triangle. Pascal was a French mathematician, and this pattern of numbers where you start with 1, 1, 1, and then to get a number you add the numbers, 2 numbers above, is something you might have come across before. So I started with 1, 1, 1. So this number, I add the 2 numbers above it. Well, I've only got 1 number above it, so it stays as 1. This number, I've got 2 numbers above it, 1 and 1, so that's 2. This, I've only got the 1 number there. Next row down, that stays as 1. This is 1 plus 2. This is 2 plus 1, and that stays as 1. And it carries on. And, I could keep on going with Pascal's triangle, but I can't help noticing that my coefficients here, 1, 2, 1, well, that's a row in Pascal's triangle, and my coefficients here, 1, 3, 3, 1, that's another line in Pascal's triangle. It couldn't, could it? What happens if we did this? So that is a plus b times a plus b times a plus b times a plus b. And that would be a real pain, but we've already got a plus b cubed, so all I need to do is to take that answer, put that there, and multiply it by another a plus b. See what you get. So I've got my a plus b cubed answer from before, and I've multiplied it by another a plus b to give me a plus b to the power of 4. And so I get my a to the power of 4. I get 4 lots of a cubed b. I get 6 lots of a squared b squared. And I get 4 lots of ab cubed. And then there's a b to the power of 4 there. And look at that. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. It worked. And we've got this same pattern in the powers of a to the power of 4, a to the power of 3, a squared, a, no a at all. And the same pattern in the powers of b. No b, b to the power of 1, b squared, b cubed, b to the power of 4. And this is great news because it means that we can predict what things like this are going to look like without having to go through all this malarkey. It's so fiddly, isn't it? And what it means is that when we get to more complicated powers, so for example 7 or 8 or 9, we don't need to bother with this. It is predictable. And so what we'll do next lesson is we will look at how we can predict what statements like this are going to look like without having to go through all this process. And I've been using A plus B, but actually it works whatever A and whatever B are. So A might be 3x and B might be -4. And it's really, really good. It's called the binomial expansion, and it's a really neat trick. So ahead of tomorrow, Thursday's lesson, why don't you have a go at predicting what A plus B to the power of 5 is going to look like without doing this. Okay, have a look at the pattern. Have a look at Pascal's triangle. We perhaps need another row in Pascal's triangle. Have a go, see if you can predict it, and I will start tomorrow's video with a confirmation that you were correct, which I'm sure you will be. Take care, see you on Thursday.